Good morning, everybody. My name is Josh Panther. I am President and CTO of Talisman, and we're very pleased and proud to be participating in the MicroPilot webinar series. Talisman, above all, is an antenna company. We started up in 2009 and since then enjoyed steady growth with the company until it was acquired by Calian Group, a Canadian publicly traded company, in September. When we first started the company, there was just GPS, and the antennas were pretty awful, and the high precision antennas were breathtakingly expensive. And at the time, there was just GPS and GLONASS, with L1 being the signal of predominant interest. And only the most expensive reference systems relied upon L2, using coherent integration techniques to extract the encrypted L2 timing. Our interest then was building better low-cost antennas and lower-cost high-performance antennas, and our interests and objectives remain the same. Things have changed. These days, there are 4 fully operational constellations in the sky, plus 2 regional systems presently providing potentially exquisitely accurate GPS timing or positioning. The available high precision has a total reliance upon a new breed of GNSS antennas with wider bandwidths, more stable phase centers, better axial ratios, and multipath rejection. This sounds like a plug, but isn't. It is true that the most important element in a precision GNSS system is the antenna. There are many variables which ultimately determine which of those antennas is the best choice for a given application. And of course, for UAVs, weight and aerodynamics are key. There are many choices. There are helicals, which are light, ceramics heavier, but having better aspects in some ways, and air dielectric antennas such as Talisman Veristar provide exquisite accuracy and better coverage for GNSS signals, and obviously greater accuracy. And of course, there are ever-increasing problems with encroaching interference. We're pleased to have the strength of the Calian Group at our back, providing, as they do, strong financial stability. However, in our new circumstances, we are unchanged, and we are pleased to have this opportunity to explain our company and explain our view of the GNSS antenna world for UAVs. Our product offerings are very wide. We have many excellent helical antennas, from single band to dual and triple band, some also having L-band corrections capabilities for reception of corrections data. We also offer helical Iridium and dual GNSS and helical Iridium helical antennas. We have many patch offerings, from small, low-cost, single band, dual feed antennas with quite respectable performance, to stacked patches with dual and triple band coverage, some with L-band capability also. And our air dielectric antennas are a little larger, but are also light, just being made of PCBs, and provide super wide bandwidth efficiency and cover all GNSS signals much wider than either the helicals or patch antennas. So virtually all of our antennas are available as OEM antennas and elements, and also can be customized to meet your exact requirements. We know that production requirements always dictate very specific connector and cable connections, and we can help with that. Our mission is to design and build high-performance antennas at a price which is commensurate with the falling price of precision receivers, without any degradation in that precision. So all of the signals from the satellites are weak, and even with these weak signals, it's quite sobering actually to see the number of satellites that can be tracked. This chart shows the number of satellites in each of the constellations. GPS became operational with 32, of which in our neck of the woods, about 6 to 8 would typically have been in view. And then we had the other constellations as they came on board. Now, at this stage of the game, we have a total of 104, with 24 from GLONASS, 22 from Galileo, and Beidou around 27. So it's a lot of satellites, and there are some very real benefits that arise from using this number of satellites. Firstly, from greater improved performance because of the better geometry, particularly in urban canyons, to accelerated convergence for PPP corrections. This diagram, or these diagrams collectively, really show the satellites in view in one instance at York University in Toronto. In these diagrams, each dot represents a tracked satellite, and the distance from the center to the perimeter is the elevation angle, with the center being zenith, and the perimeter rotation being the horizon. So first, looking at GPS only, just 9 satellites in view in this particular instance. Adding the GLONASS space vehicles brought the total to 14. Again, a big breakthrough at the time. And then added in Galileo brings the total to 19 satellites. And adding in Beidou brings the total tracked satellites to 25. And were we in a region where we could receive the QZSS from Japan or NAVIC in India, those would add more. I have to say that's a hard working piece of silicon in that GNSS receiver. So this is a little bit of quite a complicated representation of the signals from space at present. And it goes in layers, with the bottom layer covering the signals available from GPS. You'll see there's L5 at the bottom end and L2, and in the upper band L1. Then there is, we'll skip over QZSS, look at GLONASS. GLONASS is the G3 signal, which is a CDMA signal. G2 and G1 are FDMA signals that from the original definition for GLONASS. Galileo adds more signals, E5A, E5B, E6. E6 is kind of interesting for some reasons we'll talk about a little bit later, and then E1. And Beidou is very similar with B2A, B2, and B3 and B1. So the signal is complicated, and then in general they're fairly wideband signals. So it's necessary to have an antenna that actually gives pretty good coverage. Some of these signals are really quite beautiful. The European Galileo system has some lovely signal formats with very smart sideband sculpting to minimize the noise cross contamination with GPS. And the really interesting thing about both Beidou and Galileo is the plan to introduce a new high accuracy service as a free service as a signal from space on E6. So and that actually should bring a lot more applications and provide new opportunities. Looking at the choices we would face for a GNSS antenna on a UAV, typical considerations include obviously size and weight, and they speak for themselves. Helicals a little taller and don't particularly give great aerodynamics. Some ground plane effects are inevitable, and they actually are an important issue for both helical and patch antennas, and I'll speak a little bit more on that. Out-of-band filtering for potentially interfering signals is also really important. And this situation may change in the future as the spectrum changes going forward. And one of the other really interesting questions is just how much precision is necessary. Too much precision, maybe you pay too much. You pay too much for the antenna. Maybe not enough. You know, represent a threat to the integrity of your product. So it's not necessarily an easy question to answer. The one thing you can say is that using the as many signals as you can gives you more redundancy and better availability, and is always a good choice. The electrical environment when you're using an antenna is really key. The ground plane, which we're just about to talk to, is very important. If the devices are used in an OEM environment, then there usually are constraints with respect to the shapes of ground planes, the presence of plastics, and so on. And it's really important if you have a dependence on good GPS, it's important to know what they do to the performance of the GNSS receiver. It can be surprising. So first, looking at helical antennas, they're really nice little devices. They typically operate in a differential mode, and theoretically and often claim to be largely independent of ground. That is only partially true. It is true with respect to ground, but not with respect to gain, but not with respect to frequency. They do provide very good phase stability, phase center stability. They provide good axial ratio, have a small footprint, but they do have one interesting issue, which you'll see going forward. Helical antennas can cover just about all the signals. It has one thing it has in common with patch antennas, that it's a relatively narrow device, so will cover small groups of frequencies. It can't, for example, cover simultaneously everything down from L5 up to E6 at the bottom end. But you can get antennas which will cover Iridium and GPS in a single antenna. So it's a useful coverage, very similar to patch antennas in the bandwidths. Helical antennas are obviously very light, breathtakingly light in an OEM application. But the best performing antennas, which are the small diameter, taller antennas, are probably maybe 3 inches tall, 2 to 3 inches tall. So not the best aerodynamically, and which probably restricts their use to maybe copter-like applications. Every application is different, and we may be able to help in terms of actually giving you some indication of which direction to go if you'd like to talk to our pre-sales engineering people. So this is the area that I just talked about, where the helicals do have a ground effect. So the claim that they're not affected by the ground plane isn't true in this particular. And you'll see here, this shows a plot of an antenna without a ground plane, which is the black plot. And in red, you'll see the plot of the antenna with a ground plane. It's 120 millimeter ground plane. And you'll see at L1, that's the upper band, the frequency is shifted up by around 22 megahertz. And although the peak has shifted, and it looks like it's just, if you can just bring maybe it's not that big a deal. If you look at the size, if you just go to the left or go to the right of the peak and look at receiving signals at those levels, you can see actually that the roll-up is really quite significant, and would definitely not be helpful if in terms of optimizing the GNSS performance. You can do a little bit of T-tuning to help. We can tune the antennas so that they basically are low, so that when they're placed in your application, they get tuned high, and so they're on frequency for your application, and that can be done. So some changes can be made with components, but typically it would require a change to the flex connector. So again, it's one of these things that is a really good idea to check it out if you have a big dependence on the accuracy. So, and just to show you what can happen with products from one of our competitors, you can see here that same idea. But it was this particular antenna, I think, which was a wider, one of the newer wide, low helical antennas. You can see that it too was detuned high with the presence of the ground effect, but you can also see it had a considerable problem with L2, with the addition of the ground plane. So it's something to be aware of, and it's one of these situations where not all that glistens is gold. So patch antennas aren't so perfect either. One thing I will say about the helical antennas is that if you get that, if you correct for the detuning, they are lovely antennas, and I'm very proud of the antennas we have. The strong performance, we get excellent feedback in terms from our customers. And although they are detuned by the ground effect, their gain is invariant, and they do provide really sterling service. The ceramic antennas have a lower profile because they're patch elements, patch elements, and very largely planar. So we make a very wide range of patch antennas, and at the moment, all of our patch antennas are use ceramic, and these again tend to be relatively narrow devices. And there's a rule of thumb here: is the smaller the antenna patch antenna becomes, the use of higher dielectric constants is required, and as the dielectric constant goes higher, the Q of the antennas gets higher and higher, and the bandwidth gets narrower and narrower, and they get crankier to use. So there is a limit really to how far you want to go in terms of using a small antenna. They're very, very easily detuned, and tuning for your particular applications becomes very critical. So for our ceramic antennas, we range all the way from 25 millimeters, which was the standard a few years ago for GPS antennas, but we put a dual feed capability onto those antennas, and which gives that antenna excellent cross polarization. And we also make a small circular dual feed antenna, which is perfect for UAV applications. And we go to larger circular patches with a 51 millimeter patch that provides coverage for dual band, triple band, and again some with L-band reception for correction signals. However, again, here comes the problem with the patch antennas. The patch antenna is not that much affected in terms of gain by a ground plane, but it is strongly affected by the presence of the ground plane with respect to gain, as you can see in the next slide. So this we picked a very small patch here, which actually makes the effect more marked. And the patch that we chose to illustrate this with is all plastic. So without the ground plane, there is effectively no ground plane for the patch. So this shows that the addition of the ground plane, 120 millimeter ground, provides a very significant improvement in gain. And you also see a small upshift in the frequency, but that again is very minor compared with the improvement in gain. The larger housings we have tend to have metal housings, and our antennas have metal bases on them for the same reason, because with a metal base in part behaves as a ground plane and provides better performance without reference to a ground plane, or are not affected so much by the presence of a ground plane. But it does increase the weight of the antenna. Now, so one thing to be remembered is the tuning of both helical and patch antennas are strongly affected not only by the ground plane but also by the plastics, and this is a very strong effect. And particularly important in OEM applications where the antenna is incorporated into the user electronics. So the plastic radome really will cause a big effect. And we are very happy to check your product. If we get into some discussions, we can look at that. And what we do to look at that is we use the plastics that you would provide and the metal piece parts that are representative of your final product, and then we check the performance of the antenna in that configuration. And if we do that, we can pretty well be sure that the antenna you get will give you the best performance that you would need. So then finally we get to the air dielectric antennas, and this is the Veristar. And if you probably guessed, we are inordinately proud of this one. So I'll try to hold in my bragging. The interesting thing about this antenna is that it has obviously it's available in several forms, but its key feature is is very strong gain at low elevation angles. Which is something that neither the patch antennas nor the helical antennas can boast. So this guy is just great for picking up L-band corrections, because geostationary satellites typically subtend low elevation angles, certainly at elevation of angles above maybe 30-40 degrees. Latitude above 30-40 degrees. So, and they also have excellent characteristics that make them particularly useful on vehicles that have fairly large roll or pitch, so that their view of the sky remains pretty good even when they're on a fairly strong slope. So, and again, there are issues when you use them. But they are really good. Typically, the gain of these and the roll off on the gain at the horizon is about 3D better than the patch or the helical antennas. And that 3 dB is really important. As I said, for the business of geostationary satellites, and also for tracking low elevation satellites and in rolling situations. Just a point, I keep talking about the phase center. The phase center is a concept, really. There isn't just a point. It's interesting to think about where is an antenna, because an antenna tells you where you are. But an antenna is a large object. So there is a concept called a phase center, which actually is where the EM, from an electromagnetic point of view, the antenna appears to be as a point in space. Good antennas have very sharply defined phase centers, and lesser antennas are obviously less good. So this antenna, which is a little bigger, I have to say, than the helix or the ceramic, is based, interestingly, it's based on a novel realization of an Alfred loop like structure, which was first developed back in about 1940. Anyway, but it is a light antenna and very suitable for bigger UAVs, because it is just consists of PCBs, and so inherently it is a light product. And just as a final note on that, it's also a little bit more expensive. It's a more expensive antenna to build than either the patch or the helix. So this shows the gain and at the zenith and also at 10-degree elevation, and you can see how the gain holds up about 6 or 7 dBs. And then this curve is our competitors' products. The red curve on the lower of the curves, so the red curve, is the roll-off that the Veristar offers, compared with competing products that are in the same kind of class, and you'll see that those products are typically much worse. And many of them, as you'll see, have roll-offs in the order of 10 or 11 dBs, which is very significant. Now So that's talking about the reception characteristics of the antennas, but the other problem that everybody now is running into is interference. There are continuously growing demands for cellular communications, which results in expanded spectrum. And that expanded spectrum can cause a considerable amount of interference. In Europe, there are some new frequencies. In Japan, there are some frequencies down at 1500 megs, which are a potential problem. In North America, there is I think, a somewhat moribund Ligado application to install 5G networks in the old mobile satellite downlink frequency band, going as high as 1536. All of these pose a significant threat to GPS corrections. And if you look at the on the high side, Iridium also is a potential threat, depending on how close the Iridium transmitter is. And for marine applications, there is the Inmarsat uplink at 1626. These are really important because, as an example, you might look at an application might be a drone that's doing inspection, for example, of the radiated power on the cell tower. And if the drone gets too close and if that jams the antenna, who knows what the end result may be. On ships, there seems to be a predilection for co-location of the GNSS antennas with other antennas. So the GNSS antenna may find itself on the same pole as an Inmarsat antenna. And because the Inmarsat is talking to a GEO at 40,000 clicks, just 20 megahertz above the GLONASS signal, with a 4-watt EIRP signal, the potential for interference is huge. So, and then also not to be lost sight of is that the noise may not always originate from elsewhere. There is it has to be remembered that GNSS receivers are commonly accompanied by control circuits, other microprocessors, and so on. They can be the source noise themselves. And it's interesting, though, because that actually can be a very, very tough source of noise to get rid of if it's not thought about earlier. And there are some techniques for checking that out, and we would be very happy to talk to you about that. You can't have infinite rejection, and it's not possible to build a sensitive receiver that can resist an enormous interferer. So one of the things that you need to start with is how much protection do you need, and that really depends on how close the GNSS receiver is going to be to the interfering source. So is the antenna co-located with other interference sources like the things like USB 3, which is turning out to be quite a legendary source of GNSS interference. And you also need to know where your system will operate. Will it operate in Europe and be subject to that interfering spectrum, or where will it be in North America? And so there's a number of things that you need to do in terms of eyeballing, or just getting some idea of what the antenna will have to put up with. And it needs to be remembered that the GNSS antenna is the first line of defense. It's pretty well the only way that you can keep those big signals out of the GNSS system. So so it's a very critical thing if you're going to be flying in these kind of environments. The other thing to remember about this is that yes, the antenna is the first filtering components, but the other thing is that it also has to be remembered that any degradation that happens in the antenna, in terms of the signal, typically cannot be recovered by the GPS receiver. And often people believe that the GNSS receiver, with its fantastic processing capability, should actually be able to retrieve some defects or recover some defects from the antenna. But sadly, that's not true. And an obvious example, for example, let's say the antenna receives just not enough signal, then you can have infinite gain in the receiver, and all the amplifier will do, it'll amplify the little tiny signal, and it will amplify all the noise that goes with it, and you will not gain anything. So it's obvious when you look at it from just a signal point of view, but there's many other aspects of that when it comes down to the phase of the signal, and there's many applications. So I think that I've probably said enough about that. So a little bit more about the role of the antenna. We have the radiating element and the LNA really work as a kind of a team. A key reception parameter for satellites is a G over T ratio, which is a little bit complicated, but simply put, it's the ratio of the raw gain of the antenna element and the noise level. Both are referred to the input just for convenience of computing. And it's a fairly obvious thing. The gain of the antenna will determine how large the signal is that it's received, and the noise level, which is generated both by the efficiency and noise figure of the amplifier, will determine the background noise, and that has to be low enough to get a good signal to noise ratio. And once that's determined at the antenna, as I said, you cannot improve that ratio by any fancy processing in the receiver. So that really is a very big deal. If you're looking at the characteristics of the element, this is kind of a typical chart for the radiation pattern of a receiver. These are often shown in multiple forms. This one is shown as an XY graph, and they're often shown as radar plots. But this one's, I think, a little easier to read. The black curve that you can see is the gain relative to right-hand circularly polarized signals. And the red curve is the response to left-hand circularly polarized signals. And you can see for all positive and actually for some negative elevations, the antenna has significantly greater gain for the right-hand circular polarization. And that is a really key issue. You also see that the gain is a function of the elevation angle, and the elevation angle is along the bottom of the graph. That's a really key issue. So it's necessary to make sure that the antenna has a really strong left-hand circular polarization rejection. And I have to say, this is one of the things that got us into this business, really, because the old original GPS antennas had awful left-hand circular polarization rejection. So that was a challenge to us when we just got started. So and then you look at the role of the LNA. So the role of the LNA is to really filter out all the interference, but it has to provide effectively zero loss in a passband. And so a deal filter has no insertion loss, it has an infinite rejection level, and a totally sharp corner at the passbands, and you'll see that in the dotted line in the diagram on the right. And the signal above, it shows the complex signals that we deal with, so it's difficult to match that. So you can't buy a filter that's that good, obviously, but the interesting thing is you can come pretty close. So that's the filter characteristics of one of our antennas with really strong filtering, and you can see that in band we We have really strong gain, and we have about close to 100 dBs of rejection for out-of-band signals. And you can't have absolutely cliff-like skirts, filter skirts, but you see it can be pretty good. These are good enough really to bring tears to your eyes. I mean, they're quite good. So then then you look at sources of noise, because the sources of noise can be several. So if you're looking at nonlinearity noise, there's several results. I'm not going to go into this in too much detail, but you can see that you can get noise generated from both absolutely overwhelming the antenna, providing a signal which is so large it saturates the front end of the antenna. There's one degree. Second degree is that you can have signals that can combine, high amplitude signals that combine in the antenna front end to provide harmonic distortion. For example, there's a signal down in band 14 in North America, which frequency doubles quite nicely into the GPSL1 band. There are other signals which will heterodyne together. One signal we had a problem with in Texas was intermodulation products caused by a cellular signal at 2100 and another cellular signal at 900 megs. And those combined in the front end of an antenna to give us interference. So if that interference can get into the front end, as is shown as a very simple arrangement on the figure right there, then you can wind up with many problems. And so typically that's the way that antennas used to be. They're not like that now, and the products are changing all the way. So it will go from the simple strategy that you see on the right, where there was effectively no protection of the front end. And that was done for a reason, by the way. It was done because one of the big fights in the early days in GNSS was a fight for sensitivity, and that was a fight for noise figure as well. And any filtering you put on the front end of a GNSS antenna will actually give you a reduced noise figure, and it costs you C over N naught. So with improved filters now, you see the system on the right, and that filter now can be very good, so it's a new approach. That pre-filter can either be ceramic or straw filter, and I'll talk a little bit more about that going forward. And of course, there's more than just the front end to protect, because you can stop a signal at the front end, but the amplifier can still amplify those signals, and they still could be output into the receiver at relatively high levels. So it's necessary to do the protection in stages. You need to protect against the saturation and the front end being overwhelmed. You also need to actually to progressively filter out some of the residual levels of signals which otherwise would get amplified through the antenna. And in the bottom there, you see a typical structure where you'll see a pre-filter, which is the orange filter, with a gain stage, and then an F3 followed by gain section, and then yet another filter sections. And sometimes those filter sections are different. So it's quite a complex arrangement, making sure that you have covered all of the signals you might run into in different locales and in different circumstances. So the other issue really with respect to protection of the antenna is also the saturation point. Not only the saturation point of the input, but also saturation of the output, because it is the last stage in a multi-stage amplifier that actually sees the highest levels of signals, and it's important to have the linearity of that at a high level. This plot simply shows that, you know, under normal circumstances, the output power should be a flat level, which is proportional to the input power, and they're just being offset by the amount of gain. And as that starts to fall off, you obviously run into a nonlinear region. And in truth, the nonlinearity starts at usually about 10 dBs earlier than that 1 dB compression point. So there are many trade-offs. The trade-offs in the selection of the antenna. So will it be a helix? Will it be a stacked patch? Maybe, or really good in applications, the air dielectric filters. Air dielectric antennas. There is how much noise protection do you need? The environment is really key. How much linearity do you need to be able to accommodate the interference sources that you see? And we've not also talked about the group delay, and I probably won't go into that in too much detail, but once you get into very tight filtering, mathematically you unavoidably run into group delay problems where the one part of the spectrum effectively can be delayed relative to the other, which introduces noise and can be a problem. And the other issue is that the filters are interesting, because ceramic filters really will give you effectively zero temperature coefficient and are very low insertion loss, and are beautiful filters, but are relatively big and also relatively expensive, perhaps costing maybe 5 to 10 times as much as a SAW filter, a little tiny lowly SAW filter. But the little tiny lowly SAW filter will also bring with it a temperature coefficient, which means that the bandwidth you plan for has to be wider to accommodate the frequency shifts that you would see in the filtering. So so it's necessary to check all of those things with respect to the received signals. And then there's the local interference, which I mentioned earlier. So particularly with in situations where you have a lot of other electronics on board, it's really good to know how much noise the CPU is generating, how much the USB 3 particularly is generating. And it's possible to sniff for those with a remote antenna. And again, we can talk to you about how you can do that. And there are defensive measures, which is to locate the antenna as far away as possible from the local noise sources. And one of the funny things really is that in the early days, actually, and not too long ago, some major producers of GNSS receivers made GNSS receivers that actually generated in-band noise, because they never thought that the receivers would be co-located with the antennas. And the 0IF receivers that are commonly used are just natural sources for generating in-band noise. So definitely use GNSS antennas with pre-filters. Filter everything, both near and far. Be as paranoid as you like with this. It would just help. And as you build things, increasingly there are other transmitters co-located, Wi-Fi, Bluetooth, and those things. They're really necessary to make sure that we don't get got by the transmitters we put on board. And and in summary, so I'd say really we've gone through lots of different antenna types, and each has got unique features and applications. Nothing's perfect. In an RF world, everything is a compromise. We certainly believe that multi-constellations, multi-signal GNSS receivers, and the antennas that go with them provide more reliable and robust positioning, especially in the position with noise from a local source. Interference on one frequency may still leave you usable signals from a different signal. So the pre-filter is a really important thing, and as is all the other design characteristics. And probably, I think that's about all I've got to say. Thank you very much.
So we'll open the floor for some questions and answers.
Yes, we are open for questions and answers if anybody has questions. Okay.
If no one has any questions, we could.
Yeah.
Yeah.
Yes, we do. We have had a couple of questions submitted, so one question asked the advantages of multi-constellation and multi-signal GNSS. I think this is a fairly big question. The multi-constellations provides greater redundancy, and the redundancy brings a number of advantages, particularly with PPP. It provides faster convergence for PPP corrections, and it also provides redundancy in the presence of noise, if that is a key issue. And the larger number of satellites provides much better geometry. The multi-signal arrangement using dual band is also obviously a better arrangement, obviously for the reasons above, but also the multi-signals allow better estimates of the ionospheric delay, so are inherently a little bit more accurate. And they're ideal for urban canyons. So lots of advantages. They're a little bit more expensive if you're going to go to multi-constellation and multi-signals, but again, they do have some real advantages, but they are a little bit more expensive. So again, it goes back to the question really: how much GPS accuracy do you really need? Other questions we were asked is if there are what are the problems associated with using GNSS close to other transmitting antennas, these include all sorts of things: Wi-Fi, Bluetooth, LTE signals, Ligado, Iridium, and the answer is that all of those signals are potential interferers, and all of those signals can potentially wipe out the GNSS. So it really is a matter of actually knowing which of the environment you're likely to be in, and using the filters that will work against the signals that you're likely to encounter. And again, you really need to know how close you're going to be to those interfering sources, and how big those interfering signals be once they get into the antenna, so that you can estimate how big a problem they're likely to cause. So if anybody else has any other questions, I'd be happy to answer them. I hope I didn't bore everybody too much. No. So I think if we don't have any other questions, I probably would say we have reached the end of this webinar. We're very happy to answer any questions. One thing I would say is that this problem is both simpler than it seems and more complicated than it seems. Very often, it is possible to build quite complicated systems, and Lady Luck can be with you all the way, and you find that you've built a system that doesn't generate interference in band. You're not close to disabling interferers, and your application doesn't detune the antenna, and you can sail through this thing and everything works out perfectly. On the other hand, we've seen many other situations where people walk into really quite serious problems, and some of those problems, particularly when it comes to dealing with local interference, signals, interfering signals generated by the CPU or maybe USB, are insuperable and without major redesigns. And so they are things that really need to be looked at very carefully. All of this stuff is really amenable to good, solid, steady engineering, and they're all soluble. The detuning effects are very easily understood. They're highly controllable. We can pretty well drop the detuning that might be needed on a dime if we get the chance to see the effect that the detuning is causing. So it's a really well-defined field, and we're very happy to help people navigate this if we can help. And we can help people with regard to what version of the antenna would suit applications best, and also keep people abreast really of things as they come along, because we are working on new antennas which all the time, which tend to fill in the holes which are left by the existing antennas. And we're also very comfortable to help with things that are probably a little bit more mundane, but nevertheless really important. It seems to us that pretty well every application that we see requires antennas that require the cabling to be a particular way, the cable lay to be a particular way, the antenna rotation on the cable to be a particular way, and we're very happy to accommodate those, so that the antenna, when it appears out the box at our customer's premise, is exactly what is necessary, pretty well just to drop in the board as is, without any subsequent work on the antenna. So, and that actually can be a pretty useful thing to have us do, and we're happy to help. But if there are no more questions, I would leave it at that, and thank everybody for listening. Thank you.